went to porcelain, now they're ceramic insulators. Let's see, yeah, that's about it. So here's a little video or animation show. So there's the insulator, there's that shield, metal vapor shield, there's those bellows. So this is the movable end. It's closed, carrying load, it's opening, it's moving contacts, moving, fixed contacts stays fixed. Then it extinguishes the arc. This all happens very rapidly. All it takes, for the AC cycle to go through 0 for it to extinguish the arc. Also, this contact gap, the contact gap for a breaker is typically 10 millimeters, where a contactor, a little motor starter, is 5 millimeters. It's able to, have that tiny opening gap and interrupt hundreds of kV, obviously because of the vacuum, because there being no air inside. So now we go over to the 3 main causes of failures of vacuum interrupters. Number 1 is contact erosion. Like I said, each time you open and close under load, you're drawing an arc, and you're removing a little bit of contact material, so the bottle is actually getting shorter as time goes on. And that's a big deal because when these contacts are closed, there's a lot of electromagnetic force being exerted on them where they're wanting to pop open in service. The contacts are wanting to pop open. So these breakers have a wipe spring holding the contacts closed, but eventually, like I said, if the bottle wears, it gets too short, that wipe spring can't maintain enough pressure and the contacts will pop open. This is mostly a visual measurement. Each breaker manual will have a contact erosion indicator or a dot on the movable end. Once that dot's gone up in the bottle, there's some way to measure this. You'd also check contact resistance. You start getting high contact resistance measurements, or they start to get off, you'd find this. So here's just a couple of pictures where we've taken these bottles and opened them up and show examples of contact erosion. That's actually why the inside interrupter has this geometric design, because whenever you do draw an arc, you want the arc to move and not just sit in one spot and burn a hole or weld a hole in the contacts. So this geometric pattern produces a field that tries to keep the arc moving or kind of dancing around instead of sitting. This is the other design is a butt contact. So contact erosion is the number 1 main cause of failure of vacuum interrupters. Number 2 is mechanical failure. Like I said, these interrupters are only opening and closing 10 millimeters, as opposed to the old air breakers, it's 6 to 8 inches. So mechanically, these are rated for tens of thousands of operations, but just like everything, it has a mechanical life, and eventually different welds, seals start to degrade. This is also a visual check, because breakers have operation counters. Typically, I start seeing after 3,000 operations is when you start having issues with the breaker mechanism, and then the breaker's not opening and closing as fast, and you start seeing issues with the bottle. So 3,000 operations. Then the 3rd main cause of failure is loss of vacuum. As you know, most breakers are closed the majority of their life, so they have, they really aren't called upon to interrupt any faults or interrupt much load. So most of them are closed. Most operations are done during maintenance. So like I said, if this breaker is just closed for 20 to 30 years, eventually enough gas is going to leak into it. When it's called upon to interrupt a fault or open under load, it doesn't have the insulating capability to do that. And this was, before our field magnetron test set, there was just, the AC or DC vacuum integrity test, which is simply go, no go, does it have a vacuum today or does it not? You're not capable of determining the level of vacuum, not capable of determining the life expectancy. It's either good or bad. You have no idea really what's going on inside that interrupter. So a little background on this pinning discharge, the magnetron, we didn't invent that. It was a lab-based test did in the vacuum bottle factories on loose interrupters. So somewhere overseas they make all these interrupters, they take out a sample size, they take out a couple, put it in a fixed coil, get a pressure measurement. Then they put that interrupter on a shelf for 2 weeks, take it down and test it again. With those 2 points, that the pressure should get a little bit better. If it got worse, then I know there's a leak or something wrong with that. So we took that technology, and all we really came up with is a way to test these, make a field portable test set so you can test these installed in breakers. But how we do that, so with our test, we're actually able to measure how much gas has leaked inside that interrupter and tell you the exact pressure or vacuum. We can tell you, okay, yeah, this is a brand new interrupter, you have 30 years. Okay, this interrupter is halfway through its life, you have 10 or 15 years, or this one might not make it to the next maintenance cycle. This is where you need to focus your attention on changing these interrupters out. So pending discharge principle is the the science behind our test set. So here's an interrupter, two contacts sealed in a canister. So you open the breaker, opens the contacts. We're applying a high voltage across a set of opening contacts like a high pot. What happens when you do that is whatever gas molecules leaked inside there, you ionize them. So you have charged particles kind of moving around. But what we're doing that makes it a magnetron is we're applying a magnetic field across a set of opening contacts. And using the right-hand rule of magnetism, we force these charged particles across that contact gap and measure it. So like I said, with our test, we can measure exactly how much gas is leaked inside this interrupter and tell you the exact pressure. Brand new interrupters should have very few gas molecules, so this current doing measures can be really, really, really small. 10 to the -6 amps. Here's kind of an animation to showing this, our test procedure. So here's a ball, some gas molecules have leaked inside. This would be like your high pot test. It aligns everything, some leak across, as long as a certain number doesn't leak across, it's said to be good. And this is what we're doing. While we're applying high voltage, we apply a magnetic field, force all those ions across so we can measure exactly what's going on inside there. This slide is important for interpreting the test results. The test is going to output a pressure in pascals. That's the unit of measurement we use. The U.S. we're used to talk about PSI, but we're talking about vacuums, negative pressure or vacuum. So we use pascals, and so this is an equation that gives the breakdown voltage. What is the voltage necessary to draw an arc between two contacts? So this is saying what that contact gap is, kV per centimeter. A centimeter is 10 millimeters. So that's the contact gap on these breakers. It's only 10 millimeters. What it's saying with a 10 millimeter contact gap in dry air, it can interrupt 390 kV with a 10 millimeter contact gap. That's why vacuum is, so popular, so widely used in the power industry. So as you can see, the insulating capability is really high, really high. Here it starts to go down. Here's where it drops off. This is atmospheric pressure over here. Before, when you high potted a bottle and it passed, all that told you was, I'm somewhere over here, somewhere to the left of that red line. But I don't know if I'm here, or you could be right there and it'll pass high pot and you have no idea. Put your sticker on and say it's good, and then in a year or two it's going to fail. So that's the benefit of our test. This is where a brand new interrupter starts off, is at 1 × 10 to the -5. Like I said, from here to here is 20 to 30 years. The manufacturers say 20 years. I've tested thousands of interrupters, and I found that really 30 years is when they really start to fail. But if you're doing acceptance testing, all your interrupters need to be a -5 or -4 to give you that 20, 30 years. If you test, this is something I expect that's 10 or 15 years old. The -3 is maybe put in service in the early 2000s. Then this -2, it fails at -1. So these -2s is still passed, it's still good. But obviously it's approaching failure, and these are the ones we usually recommend replacing. And I use this a lot with customers that have a bunch of 30-year-old equipment. They know they need to start replacing it eventually. Really come in and test everything. The ones here, that's where your maintenance dollars need to go now. Or swap to a less critical circuit. These you still have 10 or 15 years left. These ones you don't have to worry about. So you can really come in and test everything and pinpoint and help your customer, know exactly what he's dealing with and where he's at on this curve. And then now it's also like any other test, where you come in and test it, get a data point, wait a year to the next maintenance cycle, a couple years, test it again. Now you have 2 points with time in between. If those numbers haven't changed, it's not leaking. If it's changed a little bit, now you can determine the exact leak rate for that interrupter. So this is my test setup in the lab. My test set's measuring current, but it outputs pressure. So I've taken all the different size interrupters. I puncture them with a vacuum fitting, hook it up to a turbomolecular pump. This is our fixed coil, so there's a loose interrupter placed inside of here. This is hooked up to my lab test set. So with this turbomolecular pump, I'm controlling the pressure. So I know for this size interrupter, at this pressure, I get this current. I pump it up and down, 40 data points down, 40 data points up, and I use that to program these algorithms that go in the test set. So that's just how we convert from current to pressure. So this is our 4th generation test set, Mac TS Core. Yeah.
So if we were to tell you we had a bottle, certain part number by Siemens,
yeah,
you would probably have that curve, so by
Yeah.
measuring current, you can tell us where that bottle,
So,
what the pressure is.
so that we did think at the beginning we're gonna have to make a curve for each, manufacturer. But after testing thousands of them, it doesn't really matter who makes them. Based on the diameter, based on the ratings, they all kind of use the same basic geometry.
Sure.
Obviously, some are better than others. Some are made in China, some are made in Germany. But yeah, I definitely have tested a lot of Siemens stuff. But yeah, all you need to know is the diameter of that interrupter.
Okay.
And then you select your curve. So, but yeah, it doesn't matter who makes it.
In general, can you tell how old an interrupter is based on the characteristics you measure?
Yeah. I mean, the old ones. I mean, the size of interrupters are getting smaller and smaller because the materials, clean rooms, and manufacturing process has, because obviously the '80s, that was the first shot at it. And these were big glass bottles made by hand, and they have pinch tubes on these old interrupters. Where they actually puncture the bottles, suck all the air out, and crimp it and solder it. So yeah, the older bottles are a lot bigger and usually made of glass and have pinch tubes. But yeah, testing. I mean, if I was to test it, I mean, there is 30-year-old equipment out there that's still, they had everything dialed in that day. There's some bottles that are going to last 60 years, but 20 to 30. But also on the other side, there's some that don't make it 5 years. But 20 to 30 is kind of good. Actually, 30 years is what I've found where they start to go bad. To answer your question?
Pretty much, yeah. I was wondering, question. You measure the current with a magnetic field to force the ions to move. Could you also do it by having the contacts closed and then doing whatever it should take to make them open and measure the duration of the flash?
So
Current flow?
some people do this test with it closed, and they do it between here and because we're not just forcing them across this contact gap, we're also forcing them to that shield and then around that shield, But I have seen it where you have done this test with it closed and then attach the other one to the shield. But yeah, this is how we do it. But yeah, it's definitely possible to do it with the contacts closed.
Is yours the only company that does that?
Field portable, yeah. So like I said, this is our newest test set. It's probably about 30 pounds. I have one of them downstairs in booth 4 if anybody wants to come take a look at it. The test set can store 500 tests. You can print it, hook it up to a laptop. But really what we can, how do you apply a magnetic field to a bottle installed in a breaker? Really this is what we came up with, is this flexible magnetic field cable. And in this cable is a bundle of 50 smaller wires. Applying a magnetic field is just passing current or voltage through a wire. So you have to wrap it 5 times around the center of the bottle to saturate the magnetic field. And then you have your high voltage and signal return. So that's how the test setup looks like. But then there's also a couple of breakers where you don't have access to the bottles, like the GE power back. So we have custom coils developed that drop right over, and that's our magnetic field. But that's what the test setup looks like on a power back circuit breaker. Like I said, we're breaker guys, but this technology works for anything with a vacuum technology. So this is a vacuum recloser. Here's a coil, we developed it for utilities. So vacuum recloser, vacuum switches, vacuum tap changers, we work a lot with utilities on testing those. The other part of our company is we do manufacture vacuum interrupters. This is how we test them in the lab. This is our interpreting the test results. Like I said, our test sets can output a pressure in pascals, but the 2 other things we look at is operations and wear. With those 3 things, we can estimate the life remaining or when you should worry about running another test. Like I mentioned down here, the -2s, it fails at -1, so the -2s are where we recommend replacing. So now, I started off doing this testing in the field. It was just pass fail, and being an engineer, that just bothered me. You're trending like every other piece of equipment. They didn't even want us to write down the leakage current. And, you didn't really know what was going inside that interrupter. It was kind of a magic black box, but now contact resistance, number of operations, and now mag testing, you know exactly what's going on inside that interrupter. Here's our information. If anybody's ever interested, I travel around and give demonstrations and presentations for free. So if you have any breakers or have any customers interested, I'll be more than willing to come out and demonstrate the equipment. for you. That's all I got.
Thank you.
Thanks for coming. Okay, if anybody wants a copy of this presentation, that's on our website, or you give me a card and I'll send it to you.
Are interrupters typically repaired or replaced the vacuum section?
Yeah, they're mostly replaced. We are doing some experiments right now on what's the word?
Refurb?
Yeah, refurbishing interrupters. But obviously, the interrupters that we refurbish, they can't have a lot of wear. And, we have certain candidates, but we are looking into that right now.
And this is being very presentation, but typically interrupters, do the contacts, if they're kept closed all the time, like in a 20-year cycle, 20-year lifespan, unless they're being cycled once a month, they aren't booked much at all, right?
No, so I don't know if you saw it. So yeah, the three main causes of failures, vacuum interrupters. But yeah, you're right, most of them are closed the majority of their life, so they don't have much wear. This would be something that's using a repetitive duty like a motor starter or an arc furnace. I've been to some research facilities that are running experiments, but yeah, you're right, most of them are closed. Most operations are done during maintenance, when the testing companies come out and operate it. So yeah, exactly. Most of them don't fail because of this. Most of them don't have a ton of operations. And then yeah, 20 years down the line, eventually this is gonna, because yeah, there's nothing you can do. 20 to 30 years is how long it takes enough gas to leak in.
And things, if you remove the load before you open the contacts, you have very minimal.
Yeah, that's how most people do it. Yeah. Yep, you're exactly right.
Do you folks, or does circuit breaker sales test interrupters as a service? Like, could we send you an interrupter to have some equipment?
Yeah,
and
for sure.
test them?
For sure. I try to work with testing companies. I try to stay out. I do some testing on site, but yeah, you definitely send us an interrupter, or we work with testing companies and have them do it. But yeah, we do forensics, anything. Anything you want. We've also got a big high voltage power test lab. We do a bunch of different stuff. Yeah, go ahead.
I'm guessing the downtime to ship an interrupter back to them, probably
Yeah.
cheaper just to have them come and do it.
Yeah.
The test.
Yeah, like I said, call it a demo. I'll come out for one day for free.
Most of my applications are very far
Yeah,
overseas.
yeah.
Of course, can they be down while you're waiting for it to be shipped back and forth?
Well, in my application, we have spare breakers and spare bottles, so
I
they
guess spare, yeah.
take one of the old ones out. Or do these folks rent your test sets?
ProTech and Intellerent and Electro rent. I don't know if these guys have my test set, but yeah, some rental companies. But even if you do the rental companies, I'd recommend contacting me and having you come out and do a little training, or we do a WebEx or something. It's really not too difficult to run a test, but just kind of interpreting the test results. Like I said, this is something that's just starting to be a problem, and the next 10 years, I'm telling you, these interrupters are starting to go. So I know y'all testing company guys, if y'all have some 1980s GE power racks or something with big glass balls with a pinch tube, I'd be careful. I'd really push for this. That's why we came up with this. My boss went to the GE factory in Burlington, Iowa, and saw that they had a way of doing this. Like I said, we have breaker shops all over the U.S. You send us a vacuum breaker, we high pot the bottles. If the bottles are good, we rebuild the breaker and stick those same bottles back in it, not knowing, the last thing we want to do is send you a breaker that a year later the bottles fail and it comes back onto us. So that's why everything, we use this within our own company for 10 years. Yeah.
I would imagine the worst case failure on those things, catastrophic failure when they explode.
Yeah. Yeah, if it's called upon to interrupt a fault whenever the bottle's bad. Yeah.
And then you had a molten metal and the glass.
Yeah, and then also, the other thing is, like I said, it has that tiny contact gap. And so if the bottle's bad, it's carrying, so you open the breaker, so, the breaker says it's open, but one phase is bad, it's still carrying current, unless you go out there with a, one of those non-contact voltage detectors and check each phase. But I've had where utilities gone out to rack out breakers, not knowing one bottle's bad, and it, makes it arc flash.
I had it happen in my home on a water heater. I opened the breaker outside, and I was doing some work inside, and I checked phase to phase, and looked up phase to phase. I didn't check phase to ground.
Phase was still closed.
Sorted. And I, what the hell is that? And I got phase to ground. How would you describe the technology of this pretty old technology?
Yes.
More application of math and software.
Yeah, and yeah, exactly, making it feel portable. Yeah, the old test sets were like the size of this table and couldn't be moved, and it was loose interrupters put into fixed coils. So yeah, exactly, PCs and really come up that way to test bottles. But really also when they spurred, the previous 20 years, there wasn't a need for this because the stuff was new and everything was working, Actually, there was an engineer named Leslie Falkenham that worked for Alstrom in Great Britain. He kind of wrote some papers about this, saying how there's a lot of this equipment out there that's eventually going to start failing. It's going to be a big issue, and it actually got him fired from his job. But he's got my boss going on it.
What was his name?
Leslie Falkenham. Yeah, he's the guy. He started all this stuff. Yeah, I got him fired.
We got fired because the boss probably said, "Don't nobody bring me no bad news."
Oh no, yeah, the big companies do not like us, and they like to act like they've never had a vacuum bottle fail. And, yeah, I gave this presentation at a conference. ABB guys went up to me and said, "Oh, we've never had a bottle failure," and I was like, "Don't you sell replacement interrupters on your website?" And he's like, "Yeah." I was like, "Why then?" And he just walked away. But yeah, they were pretty hostile. I was just at Doble. Siemens guys didn't like me either.
So we have
But they like the high pot. They like the 1 year warranty. They don't like that's the other thing about these interrupters. A lot of times they sit in a warehouse for 10 years, and then they get bought in surplus, and then they get stuck in breakers. Westinghouse, the first 2 digits of their serial number is the age, and I've tested a Westinghouse breaker that was 10 years newer than the bottles that were installed in it. And like I said, these bottles have a 20-30, it's a shelf life. So if you have bottles just sitting on the shelf, they're leaking.
Do they actually leak? Even the seal, here's still good. They actually leak through glass, don't they?
Yeah, exactly. Yeah, ceramic, stainless, glass. Yeah, hydrogen, helium, given enough time to enter anything.
That's why our tires will flat. Started.
Yeah, exactly.
Yeah, so
Thank you.
Thank you very much.